So in this session we are going to learn about the asymptotic notation and the big O notation. So what is asymptotic notation? In the previous session we have seen there are three cases: first case, best case and average case. So for the average case we have seen some function which is f of n, which is rate of growth, right? So as we know there are three cases, and for all the cases we can draw the function, or you can say we can get some values in fn, right? So what we are going to do is, from fn we are going to take some values and we will define one more function gn. And what are these values? These values will be approximate of fn at higher values of n. Okay, so we have defined one more function gn by using the higher values of n. And what we will do, as we know, we can just simply draw the curve for the fn, so we can also draw the curve for the gn, right? So this type of curve, and we are using one function and we are going to take the higher values of n, and then we will draw the curve for that higher value. This type of curve is called asymptotic curve in mathematics, right? So as you can see, this type of curve is going to used by the GN. So these curves, or you can say, if we say there are three cases: worst case, best case, average case, and there are going to be three GN, right? So these three GN are going to make some curves, and these curves are the asymptotic curve. So these cases, when defined in form of the curves, which are the asymptotic curve, these can be derived, or you can say these can be called as asymptotic notations. What I'm trying to say is there are three cases: worst case, best case, average case. And for all three cases we are having fn, and we are going to take some values and we are going to define gn. And for gn we are going to draw some curve which is asymptotic curve. So asymptotic curve means all three curves are going to be the asymptotic notation. So for the worst case, we are going to use the big O notation. It gives the tight upper bound of the given function. It is used for the worst case. Second is big O, big theta notation. It gives the average running time of the given function, and it is used for the average case. And third is big omega notation. It gives the tight lower bound of the given function. It is used for the best case. So for all these three cases we have got the asymptotic notation, which is big O notation, big theta notation and big omega notation. So in this video we are going to see what is big O notation. Big O notation, as we seen that it is going to give the tight upper bound of the given function. So as we said, there is a fn, right? Fn is going to have some values, and we are going to derive one more function gn from the fn, and it should have the tight upper bound of the function, means tight upper bound of the fn. Let's read this statement. Big O is for the big O notation, and then I said we are going to take the gn, right? And gn is derived from the fn. And how it is derived? There exists positive constant c and n node such that fn is greater than equal to 0, and this gn is having a constant value c which is also greater than equal to 0, also fn. And for what values? These are uh, n values which is greater than equal to n naught. What does it mean? You are still confused, right? So I said there is a function fn. Let's say we are having fn is equal to n square plus 3n plus 1. And I said we are going to derive gn function. And gn function should give the tight upper bound of the function. Which function? This one. So how we can get the tight upper bound of this function? We are going to use this value, because I must use the approximate higher values of n. So this is the higher value, right? So n square is used here in gn, and there exists positive constant c. so I must use a constant also. So I'm going to use 2. Why I use 2? Because it should be tight upper bound. Tight upper bound means it should be almost equal to these values, right? So if I see here there is 1 into n square and I just want a nearest value, so it would be 2, right? So I simply write 2 here, right? Because I just want the tight upper bound. Okay. Okay, so now I have taken the constant value c, but there is still something missing, which is n naught. So means n should be having some different values. So I will start assigning some values to the n. Let's say I start with the 2, right? So n is equal to 2, and if I put n is equal to 2 in this equation, the fn will be giving the value 11, and for gn the same n square will be giving value 8, and we must count this 2 also, right? Okay, so you can say this is still the constant, right? So we will put it aside. Okay, so now the value of the fn is 11 and gn is 8. So gn is giving the lesser value than fn, right? Because it's 11 and it's 8. Okay, so keep on giving the values to the n. So let's say I give value n is equal to 3. So I will put 3 value to the same fn, and the value will become 19. And for the gn, the value is 18 and 2 is still constant. Okay, so now you can see that fn is still having the greater value than the gn. Now I will give one more value, n is equal to 4. So for n is equal to 4, the fn is 29 after putting this value inside this function, and gn is 32 again by using this, right? So these values, now you can see the difference. Fn is 29 and gn is 32. So gn is having greater value than the fn, which was not before this value, right? Fn was greater here, fn was greater here, but here gn is having the greater value. But when this happened after this value, and even you can see that these are almost equal values. There is only the difference of one number, right? So this value is important for us, right? So we can say this n naught value is 3. Now if you read this statement, let me read this part separately. Fn is greater than equal to 0. Yes, it is greater than equal to 0 because it is having one constant value, and these values, if we are going to put any value into the n, then it must be, or it would be greater than 0, obviously. And then gn, for the gn, I'm writing equal and greater, right? So there's a constant which is 2 here, right? I use 2 everywhere, right? And what it is saying is for all n greater than n naught. So n naught is 3 here. If I say it is 3, so n should be greater. So at the greater value means if n naught is 3, the greater value is 4, right? For these values, the value of gn is greater than fn, right? So this is what I was defining here. There is a constant, there is n naught, and this gn will be greater or equal, right? For what? 3, it is almost equal, which in some cases it might become equal, but we are still assuming it almost equal, right? So this is actually satisfying this condition, right? That the gn is greater, including the constant, or equal. For n naught is equal to 3, and n will be greater than or equal to this 3, right? For all the values greater than or equal to 3, it will be what? Gn will be having greater value or equal value than fn values, right? So if we see here, if we write in this form, so O is for OGN and equal to Fn, and if I put it here, Gn is equal to n square, right? And if I write, if I see this into the form of this curve, as I said that this is the asymptotic curve, so there's an n node value, right, which is 3. Before that value, if I see the curve for the Gn, it is below the curve of Fn, means there are some value, let's say 0 1 2 3, so the value here is you can say 2, and for the Fn it is greater, somewhere 4 or 5, right? So these values were below or less than Fn values, but after the value n naught, which is 3 here, when the value is 3, it became equal here, and then after that these flipped, right? The values of Gn are greater and from greater than Fn, right? So the values of Gn are greater than Fn for all the values, whatever number you are going to write after this and not, right? So this is what we call the big O notation. Here you need to keep in mind two things. First, the values you are going to take for the C constant, it should be tight upper bound. As I said, I took the value 2, which is almost near to the n square, right? And the second thing is the values, if I say I write let me show you the chart here. Okay, so the value was n square, right? If I take the values in n log n or something in the form of log, then it will convert, or it will just simply convert the values to the lowest, right? But what I want is the tight upper bound, so the value should not go too much low value. You cannot take the lower values, you just have to take the nearest values, and you cannot take the higher values, too higher values, which can be into the form of 2 raised to power something, right? You must take the value nearest to the n square, so I took the 2n square, right? Okay.